Good afternoon, fellas. Today is the day for Upsolving. So we have Misha Short Contest 5. Only 2 out of 4 problems are solved. So we need to close it. And we'll start with problem C because it's easier. So I hope we do it fast. Also, I'll be eating a bit. Sorry for that. Okay, so we have an array. And we need to find out how many subarrays are there. We need to find out how many arrays there are with the following property. If you continue them cyclically, like this, so this element is this one, this element is this one, then these elements are at least the corresponding elements from the array. So this problem was rated 2400. However, I really don't know what to do in it. It's the text said that it was a number theory problem. And the only thing from number theory, and actually from algebra, from like inequalities, that I find applicable here is the fact that if you have AB at most n, then either A is at most square root of n or B at most square root of n. Therefore, so I can, if I have some fixed s, the length of this array, if I have fixed s, then I can find the number of arrays with this s in O of n time. Therefore, if s is at most square root of n, then I can solve it in O of n square root of n time. However, this is nice, but we also need to consider this case. And in this case, it's a bit harder, let's say. Okay. Maybe what they say about number theory is has to do something with with divisors. What do I mean by that? So, for example, assume that assume that like S is S is PQ. And then our segment of length S is actually Q segments. And if it is Q segments, then maybe we can solve the problem separately for these segments. But no, I think it's not the case. For example, if here we have number 10, and here we have number 9, and here we have number 8, then this segment loses. It loses because it's not superior. It's not superior because it's less than this element. So this element dominates this element. However, actually it's not needed because this element dominates this element. Well, maybe we can do it the other way. Maybe we can do it the other way. So how do we check that an array is good? First of all, this array should be good, but this is not enough. Is it? Well, I have one more idea, maybe. So let's assume that we have an answer for this array. What about the answer for this array when we cut one element here? So first of all, there are n segments which end with this element, and they all are superior, definitely. So the answer gets -n. However, it might also increase. And why is that? Because there might be several segments which were bad because of this element, which were not superior, but now they are good. And how many are they? So let's again assume that all elements are different, because we can. Yeah, let's assume that all elements are different. I think it will be easier for us to think about it. Okay, if we remove the last element, okay, if we remove one element, let's fix S, I think. Let's fix S. And then let's jump like this until we find the first element such that it is smaller than our element A. So this is smaller than A. So before the removal, this segment was bad, definitely. What about after the removal? Actually, after the removal, if this element is greater than A, then the segment is still bad. Yeah, this element is still bad after the removal. However, if this is S and there is no such element, okay, I think we need to draw. I think it should be another way. Yeah. So let's draw it like this, and let's fill the left side with plus infinities. So this is plus infinity area. So again, let's take A. Let's jump like this by S. Okay, so there are several elements which are less than A. And finally, there is an element which is bigger than A, and maybe there is something else here. I don't know. So how can this removal matter? So it definitely fixes this segment. This one. It definitely fixes this one. The problem is we really don't know if it fixes this segment, which is one to the left. Yeah, because this depends whether this pair is bad or not. So we're definitely sure about one segment, but not about the others. Gosh, it's hard. Okay, maybe we can do it the other way. Let's look at the first element. So let's take the first element of our array. So if segment starts here, it is not affected by this element A. So we're only interested in these segments. So we're interested how many of them are good or not. So what can we do here? So let's assume that we chose some segment. Actually, we just want to find out how many segments are there, which start here and which are good. That's it. This is what we need to do, like in O of n divided by like log, not log n. No, n divided by something substantial, for example, square root of n or 64, or maybe something like this. So, and also let's keep in mind that we're only interested in segments which are of length at least square root of n. Or maybe we can do it even this way, that we add a new element to the left. So we added a new element here. What would we like to know about this array to add this new element? So for example, we're checking the segment of size S. Then we would really like okay, first of all, we're interested if this segment is good, where here we have A. And second, so there are two cases actually. So if element B is greater than A here, then it is immediately a bad segment. However, if B is smaller than A, then we're interested if this segment is good, where it is A. Okay, you know what? I don't know how to solve this problem, and I give up. So Umnik said that that you don't need editorials at all. Well, I feel like this is false. I really need to know how to solve this problem. It's really devastating that I cannot solve this problem, and also I believe it's solved by thousands of people. But still, I really need to see the editorial. I needed to look here, then here. During the contest, not really many of them solved this problem. So it's diff1c. Well, okay. So let's fix S for every pair. What could it prove? That if subarray contains AI element, then AI must be greater or equal than AJ for every J. No. For every J starting with this I. Something strange is written here. How does d of n even matters? What? So the whole time I didn't understand the... Ah, infinite periodic array. It is periodic. All this time it was periodic. That's why it's written that it's modular n here. Oh my god. Oh my god, the whole time I was not solving the right problem. Okay, now the problem... Well, it's nice when you can read the statement only after reading the editorial. However, I am now ready to solve the problem properly. So we have a cyclic array actually. The whole array is also cyclic. A periodic subarray is superior. Okay, so there were several ways I could find this out. For example, infinite array A. And I didn't even bother to notice it. Yes, now it's definitely easy to say that if we have some segment, then actually AI should be equivalent to AJ, should be at least AJ, where I is equivalent to J modulo GCD of S and N. Also, now we cannot assume that all elements in the array are different, because it's not correct. So we can iterate over all possible GCDs. So let's choose some fixed GCD of these two numbers. Or this is some number g, which is a divisor of n. So let's fix it. Now the problem is separate for all subsequences modulo g. So let's take a subsequence modulo g. For this subsequence, actually, let me think. Yeah, let's draw it like a rectangle. So this is g, this is n over g. So we need to choose like a column or maybe several columns in such way that so in each row we can only choose the maxima of this row. Yeah, in each row we can only choose maximum of this row. And if we did it, okay, so let's do the following. So I think it's easier to unwrap it as a flattened array. Okay, so for each position, let's find the biggest subarray such that each element, so for each residue modulo G, all elements on these positions are maxima along the whole array A, or on the same modulus, or on the same residue. So all these elements should be maxima. And it's quite easy to... Well, it's not like 2 pointers, even. It's simply like, I choose this element, then I go as right as possible, and I stop. Then I again find the next maximum. I start here, and I go to the right as far as possible. So I have several segments, and then I need to take all segments of length AR where what? I need to take all segments AR where AAG, where not A, like B, let's call it B, where B is relatively prime with N over G. Okay, how to do that? I think we can do it quite naively. So let's store all these segments. Let's store all these segments in sorted order by their length. So it's the shortest length, the smallest length, it's bigger, 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 bigger. So let's go through all possible B's from 1 to like N over G minus 1, I think. Each time we like naively make the divisions, then we go on and we remove all these segments from the consideration. Okay, it should be quite easily writable. Okay, let's go. So fast TO is a must. Okay, let's go. Now we need to solve tests. And I believe it's just an array. So let's see. Let's look. Ah, it's just one array. So we will have several arrays. First of all, we try to read n and return false. If we fail, else we return true. Here we read the array. And also we'll need using vb equals vector bool. Let's go. So here we need to like print findance of a. Okay. So first of all, let's find all divisors. Okay, and then we solve the problem for each divisor. Okay, we will need, of course, long. We have long cons equals 0. We will add up it to the answer and return answer. Also, let's push for back from divisors, because the biggest divisor, we're not interested in it. Because it is n, like, okay, constant n equals a bit size, and here we put n. So the first thing is to find divisors. And it's quite simple. We go through all numbers. And if n%i equals 0, then divisors dot pushback of I. Okay, now it's simple. So if int d equals n divided by divisors I, and if d is greater than divisors I, we push back d, and then we return divisors. So it will give all the divisors in increasing order. Now let's consider one divisor, and it will be the GCD of S and it will be the GCD of what? It will be the GCD of S and N. Let's also actually calculate GCD. I think it is acceptable. So while b a% equals b, swap ab per name. Yeah. Okay. So, first of all, we need to construct a vector bool of maxima. And for that, first of all, we need to construct the integer array of maxima. Maxima of size divisor. So divisor is simply g from the solution. So we say that maxima of n% I is maximum of maxima of n% I and AI. And we need to not forget about including algorithm here, because maximum requires algorithm. Okay. Now let's go through all the whole array. So VB a big element, and big I is simply that AI is equal to maxima n% I. Not I. Actually, here it should be everywhere. It should be divisor. Great. So now it's quite simple. So we need to find the segments. So for that, we need to find any zero in our array. Let's do it. So int 0 equals big dot find big dot begin, big dot end, and false. We need to find any false. And I need to subtract big dot begin. So if 0 equals n, this means that all elements are big, and that means that all segments are big. Okay, this is the first case. Let's solve it. It shouldn't be hard. So let's go from, let's say that g, and g is n divided by divisor. So from I to 1, at most ng. So if GCD I and ng equals 1, then plus plus then ans plus equals n. So this is quite simple. I iterate over all possible lengths divided by g, by divisor. So the length of array is I times divisor. I want that GCD of I times divisor and n equals divisor. Let's divide this thing by divisor. We see that n by divisor is ng, so here we get ng, here we have 1, and here we have I. So I want I to be relatively prime with ng, and this is what I check here. Great. So this is easy. Also, let's in the end say that we continue. Okay, now we're interested in case when 0 is not n. In this case, we need to find the segments. Segments. So let's go through all I starting with 0. I is less than. Okay, we need to consider all elements one by one. That's how I'll do it. So I will start with one segment of length 0. If I have a segment of length 0, this means that currently I'm not having a segment of ones. I need to find all segments of ones. So also let's say that current is 0. Here we will say the following, that if plus current is at least n, then current is 0. Fine. So let's look at big current. So if big current, then actually we just need to increment segments dot back. Otherwise, we need to create the new segment, but we only need to do it if it is not already created. Sorry. This can be done. Okay, let's just push back 0. I think we can emplace back and it will add 0, but I will not risk. Excellent. So now we have several segments. Let's if it ends with with 0, let's pop back. Then let's sort it. Actually, I want to reverse sort it. And let's do the same thing. Okay. So in the end of the array, we have small segments, and in the beginning, we have big segments. So first of all, let's remove all small segments. So while segments dot size and while segments dot back is less than I times ng, not I times divisor. This means that our segment is too short and we need to remove it. Okay, after that, let's go through all segments. So what do we need to add to the answer? So answer plus equals, it's actually quite simple. We need to subtract the length of our segment from the divisor and add 1. That's it. Okay, I think we are finished. First of all, let's try. No, I think it's fine. Let's also try. We have a segment where all numbers are equal. I would only add some big array. One 1,619. It's not correct. This should be 2. Yeah, this should be 2. Why should it be 2? It seems not very good because 7 3 and simply 7. Yeah, it should be 2. Well, the debug should be quite straightforward. First of all, okay, let's fix that test, and then we will look at the test with 10. Actually, the test with 10 is immediately false because the answer should be no, it's correct. There are 9 possible lengths and 10 possible starts, so the answer is 19, is correct. Okay, here we need to get 2. So 1 for divisor equals 1 and 1 for divisor equals 2. So let's jump here. So divisor is 1 and sequence. It's for now it's still empty. Okay, now it has one segment of length 1. Yes, it's nice. And the answer is 1 now. Good. Now let's move on to the divisor equals 2. Let's again jump here. And we see that we have... No, this is not correct. This shouldn't be true. And this is because it didn't think that 3 is maximum of its residue. And why did that happen? It should be I here, and it should be I here, and it should be I here. Yeah. Let's restart. Well, now it works. 21690. Let's try upsolving. Well, it's not even TL. It is not even TL. Oh, it's accepted in half time limit, which is acceptable. I think it's acceptable. Well, let's move on to problem A, which is a harder one. But they promised that it's simply DSO. Maybe I again didn't read the statement correctly. So let's read it very thoroughly. We're given an undirected connected graph with 8 edges. The length of some path between two vertices is the bitwise XOR of weights of all edges belonging to this path. If it traversed more than once, then it is included in bitwise XOR the same number of times. Then we have 3 types of queries. Add an edge from X to Y with weight D. It's guaranteed that there is no edge. Okay, remove an edge. And calculate the length of the shortest path from X to Y. Well, you know what? I will again look in the tutorial because I was fed up with this problem during the contest, and this time I think I read... What? This problem happened 2 times? Are you kidding me? So this time you need to find the... Okay, this problem is also G. What? But it's definitely easier. Yeah, it's much easier than even F. Yeah, because you have one fixed tree. You have one fixed spanning tree. Okay, let's look here. So now this problem was only solved by 6 persons. Okay, bit masks and so on, I understand, but I still don't know how to solve this problem, like, what ideas are needed. Let's see. Dynamic connectivity. I am not a person who knows complex data structures, and this is like complex. Okay, let's learn a new technique, which I never applied in competitive programming. So we build a segment tree over queries. Okay, each vertex of the segment tree will contain a list of all edges existing in the graph on the corresponding segment of queries. Each vertex of the segment tree contains a list of edges. It's like persistent GSU. If some edge exists from query L to query R, then it's like an addition operation on segment LR in segment 3. But instead of addition, we insert this edge into the list of edges on the segment and we make no pushes. Then if we write some data structure that will allow to add an edge and rollback operations we applied to the structure, then we will be able to solve the problem by DFS on segment 3. Dynamic connectivity, oh my god. Okay, this is a nice idea. So we can simply store all cycles and we're not bothered by the fact that some of them are unreachable. Okay, I've read enough, I think. Well, I'm not really a specialist in dynamic connectivity, but now it seems that I will have to be. Okay. Okay. So, we make a DSU on all queries, a segment tree on all queries. And we when we enter a vertex, we add all edges which cover this vertex. Then we traverse this subtree, then we leave it. Okay. Okay. Let's try and do it somehow. So, I think we will need no, I will not need bit sets, because instead of bit set we can just use long or integer. Yeah, so structure DSU with rollbacks. Okay. How do we implement DSU with rollbacks? Well, during the DSU, we make some changes and we need to store them to undo them. Okay, so we will have some sort of state. We have some states. And we will have a vector of... So what do we store in DSU actually? So we don't have any path compression. We only have rank heuristic. So let's implement this heuristic. So we have rank. Also we have what do we have? Also we have a vector of ints, which is cycle basis. Is it called basis or base? I'm interested. Base. Yeah. What else? And we need to make some... We need to undo some operations. Also we need parent, of course. Parent. And we need a number which is called... like potential. Okay, and we need to make the basis for rollbacks. So we need a vector of something to undo our... to undo. Let me think. Okay, vector of something. I don't know what. Rollback. So rollback I is what we need to undo to get to state I minus 1. Okay? Then it means that rollback dot size minus 1 is our current state. So let's make some easy functions. First of all, void make a checkpoint. Make a checkpoint is simply rollback dot pushback and place back, nothing. So this means that rollback dot size is increased by 1. Okay, now void make a rollback. Here we do something with rollback dot back, and then rollback dot popback. Let's make also a function void jump to state int s, and while s plus 1 is greater than rollback dot size, we need to make a checkpoint. And while s plus 1 is less than rollback dot size, we need to make a rollback. Okay. So what do we store in rollback? First of all, we need to store how ranks changed. So let's include tuple. So first of all, the first thing is VPII, which stores how we changed our rank, how we need to get it back. So secondly, we need to store how we changed our cycle base. It is simply a new VI. Moreover, I think we can immediately say here that rollback.back, this thing should be our cycle base. And here we can immediately say that cycle base equals get one rollback.back. Okay, this is settled. Now let's actually consider get 0. So we don't need to add anything here, but to make a rollback, we need to go through get 0 rollback.back dot size minus 1. And we need to say that rank something is something. To do that, let's take this thing I dot first And here I dot second. This is to make a rollback. Okay, then we need to fix parent, and it's like the same thing as with rank. Two, and here we use parent. Finally, potential. A potential is again VPI, I think. Okay, it's done. It is done. So we now have basically DSU with rollbacks. It's like rollbacks but with no DSU. Now I think we can do some usual things. Yeah, let's start with add edge. So from X to Y with weight. Yeah, so if so it's quite easy. So it's like so let's find. So first of all, int find root int x. Okay. First of all, let's say that int y equals. So if x equals parent of x, we simply return x. Otherwise, we need to take parent of x, find its root, and that's it. We don't need the path compression, so it's... let's not only find the root, but also find potential. We need both of things. We need to find root and find potential. Find root and potential. So here we need to return actually the potential of root. Okay, whatever. Let's return x and potential of x. I don't see a reason why not do that. Otherwise we say pi ans equals this. And here we need to ans.second XOR equals potential of x. And then return x. That is because if we have our vertex x, we need to jump up still. Okay. Okay, whatever. So first of all, let's find the root of x and potential of x equals find root and potential of x. The same thing about y. Okay, now if Rx equals Ry, then it is easier. It is easy because this means that we have a cycle. We have a cycle of weight. Let's write it. Add cycle W XOR Px XOR Py. Otherwise, we need to add a new edge. So if rank Rx is less than rank Ry, then swap Rx Ry. Then we say that parent of Ry is Rx if rank Rx is greater than is equal to rank Ry, then plus plus rank Rx. And also we need to say that potential of Ry is what? Now it can be calculated. It can be calculated because we know the weight of the path between x and y. It's w. So let's say we know that w is what? First of all, we need to go from x to rx, which costs px. Then we need to go from rx to ry, and this has this thing as potential. And finally, we need to go from ry to y, which costs py. This means that this XOR is 0, and this means that this should be w XOR px XOR py. Okay. But this is not correct way, because actually we need to write function change potential change parent and change rank. And all of them are like the same. So first of all, let's write here that we say that change parent ryrx. So let's write this function. We say that parent of x is par, but before that we need to make the rollback. Rollback is the third one thing. So in the third one thing we say that rollback dot back get 2 of it dot emplace back x and parent x. Extraordinary. The same thing about rank, which is 0, and the potential, which is 3. So rank is 0. And potential is 3. Excellent. Okay, the same thing here. We need to say change rank of Rx to rank Rx plus 1 and change potential of Ry to this number. Okay, we also need to write add cycle function. How do we do it? So we don't need to work with rollbacks because they already work. Instead, what? Instead, we need to make like traditional Gauss. Let's go through like while C, we take find leading one of C. And then we need to like look in the cycle base for it. So if cycle base of leading one is 0, then cycle base of leading one is C. Else C XOR equals cycle base leading one. Let's write the function find leading one. And it's quite easy. So if we have GNU C, we return 31 minus built-in pop count of x, and else we do it with a cycle, not pop count, count leading zeros. And we say that if x divided by this has a 1, then return true. Return I meant. Here return -1. Okay, we have reached the function floor. Okay. I think I feel like this doesn't work for some reason, but okay. Now let's write a segment tree. In segment tree, we need to store. So in the leaves, in the leaves we need to store. So in the very leaf we have the operation. Yeah. In the leaf we have. In the leaf we have this query. And we also have segments. X, Y, D. So let's make vector of tuple of int. Vector of tuple. A. Tuple. Also we have queries, which are the length of the shortest path between X and Y. Okay, let's make another function, which is decompose. And it does the same thing. So, okay. While C, it takes leading 1. And if it is 0, then it returns C, actually. So this is what decompose does. And here, we will replace it with the following. We will say that C equals decompose C, and if still C, then we will take the leading 1, and we will put C in our cycle base. That's it. This is the correct way. Okay, then we can write the shortest path. Okay, let's write another function, minimize. Okay, what do we do here? While we have int ans equals 0, but then while C, we try C equals decompose of C, then if C equals 0, okay, we're like break. Else we take the leading 1, add it to ans, and remove it from C. Okay? Okay, then we return ans. And finally, let's find the shortest path. So we find root and potential of these two vertices. We know that these should be equal. So if Rx is not Ry, we can like throw 0. Okay, now we know that they are equal. Then we need to return minimize of px XOR py. Extraordinary. So in segment 3 we store this thing and what? And that's it. We actually don't need anything else. Okay, what then? Now I believe we need to process one segment. So let's write it. So void. So first of all, okay, we need segment 3 int n. And we replace a with of size 2n. Also we have vector VPI queries. And here let's call it segments. queries actually, let's assume that we have, that we are past these segments. So we have queries, and I think we can also take segments. Yeah. Can we take segments? No, I think we don't need them. Okay, for each segment, it's like this triple, and also, so it's vector of pair of PII and tuple. Yeah. So queries, and here I believe we need to add the segments one by one. So add edge lifetime edge. Okay, let's make the function add edge. How do we do it? Let's remove this one. So lifetime dot first plus equals n, where n is the size of queries. The second also plus equals n, and while lifetime dot first is less than lifetime dot second, we do something. So if lifetime dot first is odd, we add it to segments. If lifetime dot second is odd, we also add it. Then we divide both by 2. Excellent. Then we need to find answers, which is vector of ints. Yeah, so vi find ants works. There is a problem. When I store my tree like this, it's really hard to understand what's going on. unfortunately. So there doesn't exist such thing as DFS. Okay, I'll try my best. I'll try my best. But how to do it? Okay, I think we need like vi answer of size n. We return this answer, but before that we like recursively fill answers recursively of answer, and for example from 0 to n. Okay, also we need like this GSU with rollbacks. We need this GSU with rollbacks. Yeah? I really, unfortunately, I understand the structure of this segment tree badly. We'll need a GSU of size... Of which size, actually? Ah, we also need the number of vertices. Okay, I believe we can pass the number of vertices here. Okay. Then here we created with number of vertices. Okay, and then we will need to fill everything. So rank of size n, cycle base of size 30, I think, parent of size n, potential of size n. And here we only need to fix parent. Okay. Okay, I see. I understand. I understand. So So here we need to do the following. Actually, no, this is not the correct way. So let's put them here. Just int left equals 0 equals n. Int right equals n times 2. And while left is less than right. So again, if left is odd, then we need to fill one vertex. Fill vertex answer left plus plus. If right is odd, then we need to fill vertex answer and minus minus right. And also let's have this DSU. And actually that's it. So we need to fill vertex. We have a vertex. Now it's perfect binary tree under this vertex. And we need to fill it. Assuming that now DSU is in state okay, we can avoid assuming anything. We can just say that DSU dot do jump to state -1. So now it's an empty DSU. Okay, to do that, it's easy. So if v is at least n, then first of all we always need to. Okay, let's also say int state, and here state is -1. So we have a tree which is in state. So if v is at least, so we always put everything from this array, from array segments. Okay. So this takes so much time. For const auto edge from segments of v this okay, jump to state and then jump to state +1, I think, immediately. Well, I think we can do like this. Okay, DSU dot add edge get 0. Okay, I think const auto xyw is better. And here we also write xyw. Okay, if w is if v is at least n, then we can say that answer v minus n is DSU dot shortest path between queries v minus n dot first and queries v minus n dot second. That's easy. But otherwise we need to jump into recursion. So fill vertex answer DSU v times 2 plus 1 in state v times 2, I think. And v times 2 plus 1. Also state plus 1, I think. I think this is not needed. Instead, we can just make checkpoint. I don't think we need a state. Well, we can store it for debug reasons. Okay. But actually, it's not really needed. Okay, so this is done. Now we need to work this out. Okay, we will have segment 3. And in the end, we will say that 3 dot find answers should be returned. What do we do here? We read n and m. Then we read the graph. Also, we need n actually. So we iterate over all m edges. We read x, y, w, and we subtract 1 from x and y because we need 0 indexation. Then we read number q. And we have queries. So we read t. We actually always read also x and y. We always subtract 1 from x and y. But also if t equals 1, we also read w. Then we need to find answer for n, a, and j, and print it. Well, it's a bit crazy. I'm tired. Okay, so for each edge, we need to find out when it appeared and when it disappears. Okay, let's somehow do it. Okay, let's store type 3. And it means how many queries of type 3 we saw. Actually, instead of that, we can simply make PPI, and it would be their size. Excellent. So first of all, we can add all these edges. And for that, we need... What do we need? Also always x is less than y. I think we can make use of vector of maps, or even vector of unordered maps. Okay, vector of unordered maps. Vector unordered. So for each edge, I want to store the moment that it appeared and the weight of this edge. So vector of unordered maps, E, size n. Okay, for const auto txyw from queries. I need to add all these edges. For const auto xyw from edges, I need to say that edge from x to y appeared at moment 0 with weight w. Okay, that's easy. Okay, now we go through all queries. So if t equals 1, we need to add one more edge. So we say that exy equals queries.size w. Else if t equals 2, we need to remove an edge. Okay, for that we need to also store like segs. So this thing is called segments. Segments. So what do we do? First of all, we say that segments dot in place back. What do we put here? First of all, we need to put the beginning and the ending of our segment. Okay, the beginning was exy dot first. This was the beginning. The ending was queries dot size. Okay, and also I need to add here the edge itself, and the edge itself is also not very hard. It's x, y, and w, but not the w from here, but exy dot second. Right, and after that I need to erase y from ex. Also, I would like to do the following. If segments dot back dot first equals segments dot back dot first dot second, then I think I would like to pop back. Finally, else t equals 3, then I need to add a new query, and it's also easier. Queries dot in place back of x and y. Then I construct a segment tree of what? Of vertices, which is n, and queries, which is queries, and segments, which is segments. And then I need to find answers. And that's it. So, okay, everything is written. Everything is written. Let's copy this nice test. And we have an error. Who would think? Okay, this is obvious. Why is there an infinite cycle? Ah, what don't you like with minimizing it? Actually, I can add const here and const here and const here. But still, what don't you like? Int at memory like so our GSU for some reason is not connected. I see, because I didn't write at edge properly. No, I wrote at edge properly. I wrote at edge properly. Okay, what happened here? So can I look into parent, for example? So we have x and y, which is 0 and 4, and nothing changed for some reason. So what is the state? Rollback is of size 2. Nothing was added in our structure. So we actually didn't add edges for some reason. We didn't actually write the edges for some reason. No, here it is, we added them. We added the edges. What? Did we add the edges? So is segments like empty? Segs. Segments is not really empty, but there is not much happening. Yeah, it should be much more. It definitely should be much more. For example, there should be like 5 edges. There is only one removal. Ah, I think if we never removed an edge, we need to remove it in the end. Yeah. So it's easier, but it should be done. Okay, we can do it here. So for int I from x from 0 to n, for of y and p from y and p from unordered map, which is e. We need to segments actually do the same thing. We need to we can not do the arrays thing, but so segments implies back pi. So when the edge appeared and appeared here, no, it appeared at p dot first, then it disappeared at queries.size. And what is the edge? Edge is x, y, and p dot second. Yeah, now it should be better. One, 1, 2 is what we need here. Okay, I like it. But it's where 2, unfortunately. It's not where... Guys, it's not where 2. Did I write this... Not to say bad words? Did I write this nice problem from the first attempt? Yeah. Yeah, that's better than I thought. Okay, and I spent 2 hours on these problems. Oh, dynamic connectivity. Dynamic connectivity. Okay, I now understand some topic a bit better than I used to. Maybe that's something good. Maybe not, because it was a mess. It was total mess. And thank you for watching.